the next slide shows the evolved oxygen in the blue and sulfur dioxide in the red. What we're really plotting here are individual mass to charge signals from the mass spectrometer. We scan from 2 AMU all the way to 535 atomic mass units. So we have more than 500 of these traces going across the temperature of the mass spectrometer. And here we're just plotting a couple of them, three of them actually, to illustrate our point. So with water, the blue we're seeing, with oxygen, the blue we're seeing oxygen and then its isotope. But then over to the higher temperatures, what we're seeing in mass 34 there is a little bit of hydrogen sulfide, which is really interesting because the major evolved gas is sulfur dioxide. So this sample is pretty oxidizing, but there's also some reduced hydrogen sulfide there. And the oxygen is really interesting because it looks like it potentially could come from a compound such as a perchlorate. The one that we're looking at right now, we still have to confirm this with laboratory experiments, is calcium perchlorate. And when that breaks up, it releases both chlorine and oxygen. And the release of oxygen is shown here. The release of chlorine really ties to what I'm going to show on the final slide here, which are these very simple chlorinated hydrocarbons that we see. 1-chloro, 2-chloro, and trichloromethane, and then an unidentified heavier chlorinated compound. We're working on that. And the reason we say we don't have any, even these are clearly there, we clearly detected them. The reason we're saying we have no definitive detection yet of Martian organics is that we have to be very careful to make sure both the carbon and the chlorine are coming from Mars, for example. We have to make sure that the carbon is not coming from any residual terrestrial carbon that we have in our system. The carbon, for example, could also come from inorganic carbon, the CO2 that you saw released on the earlier graphic. And as the perchlorate breaks up, it might produce, for example, hydrochloric acid that reacts with some of the carbon and forms these compounds. So there's more work to do, but it's a really interesting study to pursue. We'll hopefully get back to other materials like this as the mission goes along. And just one final point, that in this very exposed material that is exposed to the harsh environment of Mars, there are many processes that could destroy even the organic material that we expect falls in from space. Cosmic radiation over time, over hundreds of millions of years, can destroy organics. We know there's hydrogen peroxide in the atmosphere. It can destroy organics. Ultraviolet radiation can destroy organics. So it's really going to be an exciting hunt, I would say, over the course of this mission to find early environments that might be kind of protected from this harsh surface Mars environment and really see what we can add to the hydrocarbon, the organic story. In the meantime, as you can see, we have lots of other things to look at, a whole suite of isotopes, and we'll be looking for these in different environments on Mars. So without going any further, I'll pass it over to John.
Thanks, Paul. Okay, so I just want to reiterate something that Paul just concluded with, is that the instrument, SAM, is working perfectly well. It has made this detection of organic compounds, simple organic compounds. We just simply don't know if they're indigenous to Mars or not. And so, it's going to take us some time to work through that. I know that there's a lot of interest in that, and but the point is that curiosity's middle name is patience. And we all have to have a healthy dose of that. And the reason why is I'm going to come back to our soil for a minute and try to give an example of that. As Paul mentioned, we basically took this material on and we had to do a lot of work to make sure that this was something that was sort of the garden variety typical Martian soil. We didn't want something that was adventurous because if we thought that was the case, based on our preliminary assessment using the APXS and the ChemCam instrument, if we thought we had something that was chemically going to be very difficult to work with, we probably would not have immediately put it into the machine. And instead, we went through a very long set of triage experiments to make sure that this material would not undergo a state change and maybe evolve water or something while it was in the rover. So we were very, very careful, and this took actually about a week or 10 days to work through before we could actually even do the first analysis. Now, Being hopeful then that there was no gunk that we were passing into the rover, we went ahead with the next step. And what is interesting is that if there's one sort of, if I can try to capture everything you've just heard here as simply as possible, what we've got is a globally representative material on Mars that turns out to also be a rich repository of environmental process and history. And that is basically what we're trying to do with this mission as we go about assessing habitable environments. The soil has been our sort of practicing or proving ground for what we've got. And we took something that we thought was a relatively average material, and as my colleagues have shown you, we've learned a whole lot more about it than we knew before. It is also the first fully integrated measurement for the mission in which virtually every instrument was involved in contributing towards the success of this operation. APXS and ChemCam gave us the chemistry. ChemMin gave us the definitive mineralogy, and if you go to Dave Plake's presentation this afternoon, he'll point out that there's a significant portion of this which is X-ray amorphous that Paul's SAM instrument was then able to tease apart as he just described. SAM, in addition, gives you sort of a global insight, really, into this material, which is distributed. Everybody's heard of global dust storms. Now we're actually analyzing the material. And what we learn here, what we measure locally, is actually applied regionally and globally in terms of what insight we get from that. The DAN instrument gives you a broader sense of the distribution of hydrogen or neutron-absorbing materials in the subsurface that helps flesh out the story. The science cameras, as Ken showed you, gives us the physical structure of the soil. REMS, the weather station, turns out to have been very important because we learned from the Phoenix mission that when we drop off samples, if the wind is blowing, it may just blow your sample away. So what we do is we sample the wind velocity profile over 24 hours, multiple times, to see that time of day when we have the best chance to just have the sample drop right in to the instrument, and that was 100% successful in every run that we did. And then finally, RAD, which is the instrument that gives you the radiation flux. As scientists get interested in understanding the inventory of organics that fall in from space or any other organics that are indigenous to the planet, radiation is one of the principal ways. It's a destruction pathway that takes those organics and reduces them to simpler materials, maybe ultimately even to liberate them to form carbon dioxide that we would never detect as an organic compound. Now, the important thing about that is that for the first time we have measurements of the radiation flux right at the place where we were sampling the soil. So you're going to expect to see a whole new generation of modeling studies, I think, start up from that. Okay, so now I want to move on to a somewhat different subject that we call our 3 months of terror. Everybody's seen that blue shirt moment where everybody was jumping up and down, celebrating the successful EDL system. Ours really isn't so much 3 months of terror as it is 3 months of tension. Every day we turn on an instrument. We do the electrical baseline check. It looks like it's going to work, but you don't really know what it's going to work until it's actually done a measurement. And then once you've done the measurement, you wonder how well it's done compared to all the calibration and baseline testing that you've done before you launch the spacecraft. And so each day we go through that, and as we turn these on, as one of our team members from Texas decided to call them, we have a hootin' and hollerin' moment. And everybody's jumping up and down in the science team, and we get all excited about that. But in the end, what basically happens, and with the SAM instrument in particular, SAM just comes last. It's at the end of the sample processing chain. It's also an extremely complicated instrument. It's practically its own mission. And when it works for the first time, we have a hootin' and hollerin' moment. But when it works for the second time, you get something that all scientists live by, which is a repeat analysis. You see that what you saw the first time is probably not going to go away. And then when you do the third sample, and the configuration is pretty much the same it was the first time, you believe maybe this just might be one for the history books, that this is going to stand the time of test as a legitimate analysis on the surface of Mars. That's basically where we were at with that excitement by the science team. So the nature of scientific discovery